All right, thank you so much. And hello again. It is my great pleasure to be continuing on the thread of the previous lecture on graphs and sets and moving into some more topical issues surrounding graph neural networks, which we have in the previous lecture introduced only superficially. For now, I would just like to note that I'm very happy for all the questions you had on CampusWire and Zoom, and please keep them coming. I will be sure to answer to all of them as soon as I get the time. And they already touched upon some of the very important topics, some of which we're going to cover right now, some of which we're not covering as part of this course, but I'm happy to share a lot of interesting references for everyone. So without further ado, let's dive into some more specific aspects of GNNs. And as a quick recap, what we've done a few hours ago is we've seen the geometric deep learning blueprint in action. And if we use the domain of sets and graphs and choose the symmetry group of permutations, sigma n, we were able to derive the key properties of set neural networks and graph neural networks. And as a direct consequence, we've already derived several architectures such as DeepSets and the three flavors, convolutional, attentional, and message passing of graph neural nets. So we've seen a very first example of how the geometric deep learning blueprint can help us categorize or even completely synthesize an entire field of learning on certain domains. And now, after we've introduced all the necessary components of a graph neural network, we're going to dedicate an entire lecture to important aspects of their design. And what we'll do first is I'll try to lift as many restrictions and assumptions we had before, for example, the lack of edge features. And we will study in depth one maximally potent flavor of graph neural networks. And after that, we'll dive into two very important and very related bleeding edge areas of graph neural networks that you might want to think about when applying these methods on practical problems. The first one is we've carried around this assumption of the graph structure being given to us as part of the domain. And we'll actually show that you can apply graph neural networks without knowing the graph up front. You just have to be really careful about how you go about doing that. And lastly, we will look at an algorithmic lens from which we will try to assess just how powerful graph neural networks are. We will identify some key limitations that graph neural networks have in terms of problems they cannot solve. And as a result, we'll actually illustrate some key directions we can use to make graph neural networks stronger in the future. Now, one aspect of GNN design that is potentially useful and is covered by the geometric blueprint, but I'm explicitly not covering it here, are coarsening methods for graphs. I will share in CampusWire a lot of interesting references for these kinds of approaches. But so far, I don't think we have come across a data set in graph representation learning where coarsening was actually necessary to achieve strong performance. So for all intensive purposes, we will for now omit coarsening and we can discuss it more offline. So as a recap, we have three flavors of graph neural network layers that categorize about 95% of the approaches of graph representation learning nowadays. And left to right, you go from convolutional through attentional to message passing. And as you move to the right, you're relaxing the assumptions on the underlying graph structure, increasing the complexity of the model. Whereas in convolutional graph nets, you're often assuming that edges encode for label similarities. As you move more towards message passing, your edges just become a recipe for passing data around the graph. And as a result, you can fit a broader class of problems more accurately, but you run the risk of scalability issues and overfitting issues. And specifically, what we'll focus on first are this most expressive flavor of message passing graph neural networks, because as one of the questions in the previous lecture completely accurately pointed out, you can look at basically everything we're going to talk about today as a special case of a message passing GNN. So in this flavor, we are computing a message to be sent across from one node to the other by considering as input the features of the sender node as well as the receiver node. And as a result, a message vector M is computed, which goes along that edge. And then the receiver node aggregates all of the message vectors sent to it to compute its next level features H. And we mentioned that there are a few interesting models that were early pioneers of these kinds of approaches, such as interaction networks, message passing neural networks, and graph nets. And specifically, one thing that becomes quite interesting as you scale up graph nets to this level is the fact that so far we've only really looked at node features, and I've kind of hand waved away edge features and these kinds of information because I said that the math will not change too much. Well, I do think it's very important for any application you might hit in the future, especially if it's dealing with things like computational chemistry, where edges will have very rich information attached to them. It's quite useful for you to see what a maximally expressive, maximally attributed graph neural network might look like. And as a result, I will assume this very generic set of attributed graph data. We will start off with, as before, assuming that I have some node features, xu, in each one of my nodes. And I'll just keep going the analogy to computational chemistry, because there you can easily reason about what could be good node features and so on. So if your inputs are molecules, you can expect the different nodes to correspond to atoms. And therefore, the node features could be the atom type, the atom charge, the number of hydrogens connected to it, and so on and so forth. Then we can move on from node features and also incorporate information at the various edges. And I will denote edge features by X subscript UV for the edge connecting node U to node V. And in the case of chemicals, you can think of edges being bonds. And then you could say, is this a single, double, triple bond? Is this bond located in a ring? And so on and so forth. Lastly, and sometimes quite usefully, we could also attach flat features to the entire graph. And this is what the xg vector is corresponding to. So it's exactly one vector on the level of the entire graph. And it represents some global attributes of the graph. In the case of chemicals, this could be, say, the overall molecular weight of the molecule, or maybe some fingerprint information that identifies key structures in that molecule, or something like this. And you go from input features as a result of applying graph neural networks. We typically want to go towards latent features that we can then use for all kinds of classification and regression tasks. And therefore, for every x, there is a corresponding h. So starting from the x's, we're going to compute the h's as the result of applying our graph neural network layer. Now, one thing I will note here is that even though I've praised this as the maximally general attributed graph neural network setting, it is actually possible to go even further than this. And the key assumption here was that edges only ever connect two nodes together. In principle, edges can connect multiple nodes together, and you get what's called a hyperedge, and the corresponding graph is called a hypergraph. And you can imagine many cases where it's not just pairs of entities that are related, but actually triplets or 4 tuples or something like this. But one thing that is going to become evident as you study such models in more detail is that even when you do have a hypergraph, you can carefully rewrite the way in which you do the message passing and the way in which you set up the nodes, such that you can model hypergraphs often using the blueprint that we're about to show you. So even though it's possible to go beyond, for all intents and purposes, this setting will be enough for now. And specifically, we will define a general blueprint for a spatial message passing graph neural network, which will generalize all of these 3 flavors we talked about before. And just as a personal preference, I'm going to choose the graph network model from DeepMind to describe this, because it operates over generic attributed graphs by design. Like, it starts by assuming you have all of these features as inputs and that you want to maintain all the latents for all of these different elements of the graph. Most other message passing layers being proposed will, for example, assume that there are no graph level features, or there are no edge level features, or you don't need to maintain edge latents or something like this. And the overall data flow we're going to follow one step at a time is, once we have all of those inputs for nodes, edges, and graphs, we're first going to update what our features in the edges are based on the features of the whole graph and the relevant nodes adjacent to that edge. Then once we have updated edge features, they can be propagated into the nodes that are receiving them, just like we did before. And finally, once we've updated both our edge and node features, we can use the permutation invariant part of our geometric blueprint to update the graph features using an overall combination of nodes and edges. And as always, we will make extensive use of these skip connections. So we'll often be feeding the previous input of a particular node, edge, or graph as an extra input when computing its corresponding latent, just to make sure that by doing all of these aggregations, we haven't lost a lot of information. So first thing we do, update the edge features based on the graph features and the relevant nodes and the skip connection. So in this case, I'm going to update my edge features into latent features HUV using the individual features of nodes U and V, which naturally belong to this edge, the features that edge had before, and the features on the level of the graph. So this makes extensive use of all of the information we have pertaining to this particular edge. Once we have updated our edge features, we can then send those as messages towards the nodes, and therefore update the node features using basically something very similar to the equation we saw before. So we are updating the node features based on a combination of that node's previous features, which is the XU, the skip connection. Then based on the aggregation of all of the messages that are sent to it, and as we said here, the messages are the edge features. So we just perform some combination like sum or average or max over all of our incident edge features. Now this is once again really important that this aggregation is permutation invariant, because if it's not, we're not going to be able to guarantee equivariance of the whole layer. And finally, we put the graph features in once again, because in principle, the graph features can condition everything. You can even think of them as one node which is connected to all the other nodes, and it stores the features for the entire graph. And finally, once we have updated both the nodes and the edges, we can now use those to update the features on the level of the entire graph. And once again, I'm using the skip connection, so HG will depend on XG, but also it will depend on the aggregation of all the node features and the aggregation of all the edge features. Once again, we need to do this in a permutation invariant way, otherwise our entire layer will not be permutation equivariant. And as mentioned already, a very similar formulation which achieves more or less the same outcome is if you don't have the graph features, but you invent an extra master node, which is connected to all of the other nodes. Okay, so these three equations completely specify the graph network model, and pretty much any spatial graph network you can come up with can be expressed with the right combination of functions psi, phi, and rho for updating the edges, the nodes, and the graph. Okay. Now let's pictorially see what's going on here. So imagine I have some features on the level of my entire graph, that's the XG, and I have an edge in the graph that connects node U to node V, and I have features XU and XV in those two nodes, and I also have features XUV on the edge connecting them. Okay, so the first step of the graph network pipeline is updating the edge features based on all the relevant nodes in the graph. So we invoke the function psi based on the features of the two nodes, the features of the edge, and the features of the graph to compute the updated features of that particular edge. So we go from X to H on every edge in isolation. Okay, now once we have computed the updated edge features, we can aggregate all the edges that come into a particular node to update the node features. So in the next step, we update the node features based on the previous features of that node, the features of the graph, and the aggregate. That's why I put the O+ in here, the aggregate of all the edge features that go into this particular node. And as a result, the function phi will give us the corresponding updated node features. Now, once we have updated the node features and the edge features, we can now use them to update the graph features. And the graph features are updated through a combination of the previous features of the graph, the aggregate of all the node features in the graph, and the aggregate of all the edge features in the graph. Once again, I put the O plus to signify that this is actually aggregated over all relevant nodes and edges. And these aggregates, together with the previous graph features, go inside the row function to compute the updated features of the graph, HG. Now, the key part here, so this specifies the entire data flow of the graph network model. The key point here is that we have extensively featured the geometric deep learning blueprint in all of these different links. Specifically, every layer which doesn't involve an aggregation was equivariant, and every layer that requires you to aggregate nodes, edges coming into a node, or all the edges in the graph, or all the nodes in a graph are invariant to permutations. And therefore, basically, this entire computational graph that you needed to do can be completely expressed using the building blocks that we have already put forward in the geometric blueprint. So even this most expressive graph neural network spatial architecture can be put together using the building blocks we already discussed. And one thing that I think is a very important exercise to do is think about how would you specify the functions psi, phi, and rho to obtain your favorite graph neural networks in the literature. For example, graph convolution nets, graph attention nets, message passing neural nets, but under the assumption that edge and graph features are given and should be processed. So most of these graph neural networks have been previously proposed without the explicit assumption of edge features. And therefore, this is an interesting exercise to see how you could use this graph network blueprint to extend them to handle edge features, but still have the same computational spirit. Okay, so this hopefully gives you a view of what's the most generic computation I can do in a message passing sense. And as we will see, this generally is sufficient to express pretty much any architecture that you can come up with in graph representation learning. But one very important point that we've completely avoided so far, and I think is really important to address, is something that at first glance might seem super innocent. Like we assume that the edges are given to us, that the ground truth graph is given to us, and as a result, we don't have to worry about it at all. We just use it as it's given to us. However, we will unpack just now how far from innocent this claim actually is. And the fact that in many cases we have to be very careful about what the graph is will lead us into an emerging area of graph representation learning known as latent graph inference, and which is something that, in my opinion, is going to probably become one of the most important areas in graph representation learning in the years to come. In practice, even if I give a graph to you, it may be completely suboptimal for the task that you are doing. And one very simple example of this is if you want to do connectivity queries on a graph. So I give you a graph and I tell you 2 nodes. I give you features in 2 nodes to tell you, I want to know if these 2 nodes are connected. So you need to answer a yes or no. And if you use the original edges of the graph, you can imagine how there could be a very long path between 2 nodes. So in order to answer that connectivity query correctly, you need to run a big number up to linear time message passing steps. And this is something that is potentially really hard for GNNs. But if you've taken a algorithms or data structures class, you might know about data structures such as the disjoint set union, which represent connected components in a completely different way, which is dependent on the edges of the original graph, but uses a completely different set of edges. And if you use that particular set of edges, you're able to answer connectivity queries in almost constant time in an amortized sense. So actually, the choice of edges you do can make a huge impact on how efficiently you can solve your problem. So this is just from a computational perspective, not even talking about what's the ground truth connectivity that we should be looking at. And we can take this to the extreme. Like, okay, we could be given a graph that's suboptimal, but maybe we can still work with that. But what do we do when there's no graph to begin with, but we assume that one should exist? So in this case, we can assume that we're just given a node feature matrix, just like we did when we dealt with sets, but there is no adjacency matrix information. We'll also ignore edge or graph features just to keep things a bit more simple, but they can also be included if we have them. And we've actually, through the previous lecture, already seen one solution on what to do in this case when there is no adjacency. Specifically, the DeepSets model is one possible solution. You can just take a super pessimistic approach and say the graph is completely disconnected, and I'm not going to model any kinds of connections between the nodes. So in this case, we can assume the adjacency matrix is the identity. So nodes are only connected to themselves, or equivalently, the neighborhood of a node is just that node itself with nothing else. And therefore, we can see that aggregated neighborhood features, the thing that we keep doing within graph neural network layers, are equivalent to just the receiver node's features, and therefore it's equivalent to the skip connection, which we had in our model before. So any graph neural network flavor, regardless of whether it's attentional, convolutional, or message passing, amounts to DeepSets under such a graph. So if you assume your adjacency matrix to be the identity, no matter what graph neural network you use over that graph, it's going to end up being DeepSets. Like the final features of every node will be computed conditionaled only based on the particular node's features. Okay, so we could just call it a day here and say this is enough because DeepSets are universal approximators. However, usually this will discard some very critical information that we'll need to get things done, actually. And there is a diametrically opposite option, which arguably is the most popular one, and for small enough graphs is probably just what you need. And that's the so-called lazy approach of just assume upfront that the graph is fully connected. So every two pairs of nodes are connected with an edge. So in this case, you can represent the adjacency matrix as a full matrix of ones, which can be represented as an outer product of a one vector with itself. Or equivalently, the neighborhood of every single node is the set of all nodes. Now, since I'm assuming I'm not giving you any edge features that you can use to distinguish these pairs, convolutional graph neural networks over the complete graph are going to have to be equivalent to DeepSets. And I think it's a very useful exercise for you to try to prove this. So show that if I assume the graph is fully connected and I assume there's no edge information, a convolutional graph neural network will end up doing exactly the same thing as DeepSets. So if we do conv GNNs, we haven't really moved from the status quo of using DeepSets in the first place. So what we need to do over these complete graphs is use a more expressive flavor of graph neural networks. Let's take a crack at attentional networks, attentional graph networks. Well, if you remember the expression, we compute our updated features h as some function over the previous features of that node, and the aggregated weighted combination of all the neighbors, where the weights are computed by an attention mechanism. And in particular, here you aggregated this attended combination over all the vertices in the graph. So the neighborhood is all the vertices in the graph. Now, if you've done certain kinds of, say, natural language processing, you will have probably seen an equation that's very similar to this before, like something that for every pair of nodes computes an attention coefficient and then aggregates based on those attention coefficients, something that was locally transformed. Well, you've probably guessed it. I've just described the transformer to you. And actually, under this lens, transformers are a special case of graph neural networks. The equation of what a transformer does is exactly a fully connected graph over which you're running an attentional GNN. And this is part of the reason why transformers are as popular as they are. It's simply because you can use them to strike a good balance between the maximally expressive message passing flavor and also something that you can scale because you're only computing one number per every pair of vertices. And the thing which might seem confusing at first is transformers were originally proposed to model text, like sequences. So how does it make sense to apply them on a graph structure? Well, the way in which the positions in the sequence are injected into a transformer is not done through the computation of the neural network. It's done by adding extra features, okay? These so-called positional embeddings, which are a complex combination of sines and cosines that tell you what position is this node in the original sequence. So the thing which makes transformers sequence-based has nothing to do with the function that they compute. It's got everything to do with the features you put in the nodes. If you drop those features, you end up with a fully connected graph attention network, just as usual. So transformers have a very deep connection with graph neural networks. In fact, they can be seen as a special case. And another very important point as to how this relates to inferring a graph to use is that because every attention coefficient will give you a scalar value for an edge in your graph, you can think of an attention mechanism as inferring a soft adjacency matrix over your nodes, right? The stronger the attention coefficient, the stronger the influence between the two nodes, and therefore more likely that you might need to draw an edge between them. So in effect, these kinds of approaches just let the graph neural network choose its own edges. If you'd like to read a bit more about the deep connection between transformers and graph neural networks, Chaitanya Joshi has put out a really useful blog on this topic, which he published in The Gradient. It's called literally Transformers or Graph Neural Networks. So I invite you to check that out if you'd like to explore the connections a bit more deeply. Now, okay, let's recap what we've done so far. We've looked at DeepSets as an option to do reasoning over an empty graph. And we've looked at something like transformers as a method to do reasoning over a fully connected graph. Now, these are both at extremes. The empty graph ignores a wealth of information, even though it's super efficient to implement. The full graph, because it's quadratic space and the neighborhoods get larger, it can be much harder to scale or extrapolate with it. So the truth, like the kind of best agnostic approach, lies probably somewhere in between. So what we want to do is actually figure out an adjacency matrix A somehow using a neural network ideally, and then use that adjacency matrix as hard edges for a graph neural network. And this is what we commonly termed latent graph inference. And it's a super, super, super hard problem because choosing edges, like committing whether or not I'm going to use an edge for my graph net, is a discrete decision. Like you either put an edge or you don't. And the problem with that is that the moment you have to make a hard decision inside a neural network, backpropagation becomes much more weird to do because these kinds of operations are typically not differentiable. And what I will do for the following 5 to 10 minutes is outline some recently proposed ways of choosing hard edges, but also being able to backpropagate through those decisions. The first option, which is a paper on neural relational inference from Thomas Kiff, Ethan Fetaya, and others, is taking a very probabilistic approach to the whole thing. So if you've come across some kind of Bayesian learning or variational learning before, you'll have heard about the concepts of a prior and a posterior. So especially a prior encodes some prior assumptions that you have about your objects. In this case, the objects are edges. And the specific things you want to model is what's the probability that the particular edge exists. So what's the probability that the adjacency matrix at UV is equal to 1? And you can specify upfront a prior distribution saying, what do you believe is the probability that a particular edge will be 1? And already at this stage, you can promote the resulting graph structures that are sampled from this probability to be sparse by just setting the probability of no edge to be very high. Now, what you do in this approach is you then run a graph neural network over the fully connected graph, which has node features XU as before. And if you remember, what the graph network does is it updates not just node features to HU, but it also computes edge features HUV and graph features HG. And in this particular case, the NRI model uses these HUV vectors, the edge features, to decode a posterior probability distribution. So having observed the X's, I can update my probabilities of different edges existing by just running some neural network followed by a sigmoid or a softmax over these edge features. So basically, this updates my probability that a particular edge exists based on the features of that particular pair of nodes as derived by a fully connected graph network. Once you have a posterior like this, you can sample edges from it. So you can just sample like flip a coin, and if what you get is yes, then you take the edge, otherwise you don't take the edge, and the probability of flipping heads or tails is specified by the value that comes out of the posterior. Once you've sampled these edges, you can use them for a second graph neural network to compute the outputs that you care about. And at training time, you can actually backpropagate through such decisions by using the so-called Gumbel trick, which heavily relates this kind of approach to variational autoencoders, or VAEs. And basically, the idea of the Gumbel trick is at training time, you don't make any hard decisions. You take a little bit of every edge, and you use the posterior probabilities to scale up how much you take of every single edge. So at training time, we actually do fully connected graphs through and through, both at the encoding part and coding part. And then at inference time, we can actually sample graphs out of this. So this is a schematic of the layers employed by NRI. You can see the encoder part, which computes node and edge features repeatedly, and then from that it derives this posterior probability of every single edge in the graph, whether it exists or not. And then this dashed line says you sample some edges based on this posterior, and then those edges are used as edges for a graph neural network that computes any outputs that you might care about. Now, this gives us a nice and probabilistic way to reason about the graph structure, but it hasn't solved any of our scalability issues, because to compute the edge probabilities and everything, we still needed to run over a fully connected graph neural network. So this doesn't necessarily fix our problem of wanting sparsity or wanting better scalability. So what we want is to actually infer a sparse graph without ever running on a dense graph to begin with. And this is something that makes it super tricky. And the current workhorse behind many approaches proposed to do this is the k nearest neighbor, or GNN graph. The way in which this approach works is if you maintain features HU in every one of your nodes, you connect those nodes only to their k nearest neighbors in the H space, for example, based on some Euclidean distance metric. And this tends to be, with some modifications, the principal way in which latent graphs are sparsely inferred nowadays. It's still very much an open problem as to can we, or even should we, do better than this. Specifically, k nearest neighbor graphs are reasonably decent to implement, and they can be reasonably scalable. However, they obviously don't represent the ground truth data structure. And in some areas, what we care about is less the downstream predictions and more the actual graph that was used to make those predictions. I anticipate that in biology or medicine, this would particularly be the case. So certainly this approach doesn't give us ground truth graphs. Like, it gives us some k-regular graphs which reasonably cover the nodes in a sparse way such that you can propagate information where it needs to go in the fastest way possible. And if you set up those k nearest neighbor edges reasonably enough, information will travel along the graph how you want it to, and you'll get really good performance. So there is this big question of, is it possible to do better than this in the general case? And even if it is, should we bother with it if we don't necessarily care about interpretability, but just the stream performance? That being said, I will outline 3 different ways in which you can use k nearest neighbor graphs to support inferring latent graphs and doing machine learning on top of them. The first one, the dynamic graph CNN, or DGCNN, uses the dot product between the nodes or something similar as a measure of how similar 2 nodes are. So the more these 2 node vectors point in the same direction, the bigger their dot product is going to be, and therefore the bigger the chance that they are going to be connected. And once you've computed this, at every graph neural network layer, you can recompute what your neighbors are for every node, just the top k nodes with which you have the highest dot product. And now that neighborhood can be used as edges for the next graph neural network layer. This is a super convenient approach implementation-wise because it's non-parametric. There's no additional parameters you're using to infer the graph. And even though it's this simple, I'm going to show you a visual example for why it is still powerful. Specifically, here on top is the schematic of the original DGCNN architecture when it was used for point cloud inputs. But what I really want you to focus your attention on is the figures at the bottom, especially in point cloud data where points have their X, Y, Z coordinates as features. You may be interested in classifying different parts or segments of an object, or classifying an object. And imagine you want to classify this table or this chair, and it's known that it has to have a certain number of legs, and those legs have to have a certain number of certain kind of shape. If you just use Euclidean distance to define your graph in the original XYZ coordinates, you get something like the picture on the far left, where for a particular point in the point cloud, which is marked in red, you will have this like diffusion spreading from like the nearest regions and so on onwards to the rest of the table. And I hope you can immediately see how this is not the most effective way of inferring semantically what's going on, because this leg will just see the rest of its leg, and then it will slowly propagate to the rest of the graph. And as a result, you will know that the object has a leg, but it won't tell you anything about the layout or configuration of the legs, which can be very useful for classifying a table against classifying a chair, for example. Whereas if you have these two legs that are symmetric, they could be far away, so messages may not reach them easily if you do pure positional distance to infer edges. If you instead do first the graph neural network layer in the local point proximity space, and then infer a new graph based on how similar the resulting feature vectors are, you could actually end up with something like the figure on the middle right, which actually has this point only like sending messages across to the same points on the other leg, because spatially they might be far away, but in terms of the actual features computed on top of them, they will end up being very similar because they're structurally very similar. And I hope you can see how just this simple modification can help you a lot to classify what's the underlying object, because unlike just blindly propagating information in spatial wise and going as far as possible there, this kind of approach will immediately allow information in one leg to send information to the other leg. And as a result, you can quickly, robustly conclude that the object has this many legs, the legs are arranged in this particular way, and you can very quickly and more accurately predict that indeed you are looking at a table. On the right-hand side, you can see a similar kind of analysis for a node that's on the edge of the table. Once again, using the semantic information of the intermediate latent vectors and connecting the graph only based on them will actually allow you to have a much better feel for what the neighborhood should be, because the node on the edge will only attend to other nodes on the edge. So you can get a much better feel for the shape of the object, as opposed to just doing pure Euclidean space diffusion, where this node at the edge of the chair will pretty much spread everywhere else in a kind of diffuse manner. So hopefully you can see how even with a purely non-parametric model, like just take the k closest points to me in the output h space, you can already strengthen predictions of these graph neural networks substantially. And things start to get even more interesting when you actually include some parameters in there and try to train them in a particular way. One popular approach that was recently proposed is reinforcement learning. And it actually makes a lot of sense because since we're making discrete decisions and RL is all about sequential decision making, it aligns up reasonably nicely. So once again, in this differentiable graph module paper by Anis Kazi and others, you can use these like dot products or something as a measure of how similar two nodes are. And then at every graph neural network layer, you can say the probability of some edge existing is proportional to some function over a dot product of some transformed features of U and V. These psi and phi can, by the way, be something like the key and query functions of a transformer. So very often this will be implemented as a transformer. And once you have these probabilities, rather than just taking the top k probabilities like what we did before, you can use these probabilities as a policy function for reinforcement learning. So an RL agent selects k edges, and the probabilities by which it selects them are governed by these p's. And once you have selected a certain set of edges, you run a GNN over them, and you keep doing that again and again and again, and you make some downstream predictions. And okay, you can update using standard gradients. You can update through the edges you've selected, but it's also useful to reward the RL agent itself for what it's done. And for that, you can, in absence of any other information about how faithful your graph is, you can use some accuracy measure or some other downstream performance you got as a measure of how good were your edges. And that part can be optimized using your standard policy gradient methods such as reinforce. And this is, once again, a schematic of what happens within the differentiable graph module. You start up with some node features, and the graph feature learning module updates these node features. And then based on them, you look at pairwise similarities to figure out what are the top k edges I should select from every one of my nodes to have this probabilistic subgraph. And then this RL agent's actions go into the second layer of a graph neural network as these specific edges that were selected. Lastly, in a very specific case that you actually have some beliefs about what the ground truth edges are, or at least some estimates on which edges might be useful, for example, as rollouts of a data structure over your data, you could directly supervise your edge choices, your policy function, to imitate the edges that you know. And this is what we did in our pointer graph networks paper, which was published at NeurIPS last year. And rather than just learning to blindly imitate the edges that were given, we found that such a model, especially when extrapolating, can deviate quite a bit from the ground truth edges. It actually learns to take this guidance, take the good parts of it, and then specialize some parts of it to be, for example, more amenable to GPU computation, because these data structure rollouts were often derived with a CPU in mind. And here is the layout of the architecture. Unfortunately, I don't have a lot of time to dive into the specifics of it, but I would invite you to take a look at the paper if you're interested. Okay, the last topic I would like to cover today is on the area of the expressive power of GNNs. So as we've seen, both by the scope of the scientific and industrial applications of GNNs, they're a super powerful Swiss Army knife for processing real-world graph data. But this doesn't mean they will solve any task specified on a graph accurately. And one canonical example that we use to assess this power is the decision of graph isomorphism. Specifically, we ask, can our graph neural network distinguish two graphs that are not isomorphic? So if I say compute graph features as part of my graph network architecture, can I guarantee that for two different graphs, I will get different vectors? Because if I cannot do that, any task that deals with discriminating these two graphs is hopeless, because I'll have to attach exactly the same label to both of them because they have exactly the same features. And that's why we often in graph representation learning use graph isomorphism testing to assess their expressive power. So we check what are the graphs that these graph neural networks are able to distinguish. And to make this very formal, we're going to study a very popular graph isomorphism test, which is the one Weisfeiler-Lehman test. And it corresponds to a simple but very powerful way of distinguishing non-isomorphic graphs, which is to just pass random hashes of sums of node features along the edges. And you basically keep iterating this coloring procedure until the hashes don't change. And then you stop and output a histogram of the colors you get. And if the histograms of the colors are the same, you say the graphs are possibly isomorphic. Otherwise, you say they're not isomorphic. So just to illustrate this, let's run the Weisfeiler-Lehman test on this particular graph here. Initially, I'm assuming a very featureless setting. So every node has exactly the same feature, which I'm coloring blue. OK, as a result of applying one hop of the Weisfeiler test, I can see that I have two cases. Either a node has two blue neighbors, or it has three blue neighbors. And in those two specific cases, I will end up with two different colors. So after one iteration of Weisfeiler-Lehman, I will have three nodes that are colored green, and I will have two nodes that are colored, say, yellow. Note that the exact choice of colors isn't important as long as we use different colors to denote different things. OK, now thinking ahead as to what might happen in the next iteration, you can observe we have some green nodes with one green and one yellow neighbor. We have green nodes with two yellow neighbors, and those might be some special cases to consider. So the yellow nodes actually have exactly the same local neighborhoods, so they will stay the same color, which we can now call red, for example. And the green nodes have two cases that branch off, one which changes to like the purple color for the top node, And the two bottom nodes will stay the same color, which now we can call gray. And if you try to run the Weisfeiler iteration one more time, you'll actually see that the colors do not change anymore, and you can just stop and output a histogram. So you have 1 purple, 2 red, 2 gray. Okay. Now, if I were to run the Weisfeiler test on something that I know is isomorphic to this graph, for example, this graph below, you can stare at these graphs for long enough, you'll see that they're exactly the same. And you can see that running exactly the same procedure will yield exactly the same histogram of colors. So as a result, the Weisfeiler test stops and says these two graphs are possibly isomorphic. It hasn't been able to attach them a different representation. And because all we're doing here is passing these injective combinations of hashes along the edges of the graph, there was a very clear connection to be spotted to convolutional GNNs, and it was spotted very early, actually, already by the graph convolution network paper of Kipf and Welling. And it also gives a pretty good justification for why, and this is very unique to graph representation learning, I think, untrained graph neural networks can work really well and be a super strong baseline, because untrained graph neural networks already correspond to passing random hashes along the graph, because it's in principle, the weights of the neural network are sampled at random. So it seems like a very powerful and very simple layer of a graph neural network, this Weisfeiler test. And it's important to note that, we do know that graph isomorphism is still not known to be solvable efficiently. So there are certainly cases where this test is going to fail. And here I've given one very simple case where the Weisfeiler test will fail. It cannot distinguish a 6 cycle from 2 triangles. So the red graph and the blue graph would not be distinguishable by the Weisfeiler test. And this is an example that is very important. We will revisit it in a few slides' time. Just want you to keep in mind that the test does fail in some very simple instances. So, okay, I said the test fails for some really simple graphs, and I've said that it can be linked to a randomized graph neural network almost. So it might be surprising for you to find out that graph neural networks are actually no more powerful than this Weisfeiler-Lehman test, at least over discrete features. So we're assuming no continuous features in the nodes. The graph neural network cannot do anything that the Weisfeiler-Lehman test cannot do. And in fact, there's a very strict condition on achieving this maximal expressive power. You want your aggregation function to be injective. In this particular case, with discrete features, you want to be summing them up to achieve this effect. So if I have this like neighborhood of 4 blue nodes and 2 red nodes, taking their sum will preserve the information about the cardinality of all of the different nodes, and that's important. If I take the average, it will tell me something about the distribution, like the ratio between the blues and the reds is 2 to 1, but it doesn't tell me about the exact cardinality, so I've already dropped some information. And taking the element-wise maximum will eliminate any multiplicity information and just tell me I have a blue node here, I have a red node here. Know that in this case, this is basically equivalent to keeping the blues and the reds as one hot features. And the graph isomorphism network paper, or GIN for short, has studied this exact setting and as a result proposed a simple maximally expressive graph neural network that follows the principle of using injective sum aggregations to achieve this result. Okay. Now, of course, this isn't the whole story, because just because I said that graph neural networks can never achieve a bigger power than this test doesn't mean we cannot analyze the failure cases of the test to make graph neural networks stronger. And this area, which sometimes is called higher order GNNs, is a super active area with many interesting open problems. And we can start thinking about them just by looking at the case that I showed you before. So the case of the 6 cycle versus 2 triangles. And specifically, GNNs cannot detect closed triangles, because if you look at the specific case and the perspective of what a GNN sees in a particular node's neighborhood, they will see exactly the same neighborhoods with exactly the same cardinalities. So to the GNN, all the nodes will look the same. I will let you think about some ways in which we can fix this. And I will give one way, which is the simplest possible way to do this. And it's as trivial as just put a random number, a randomized number feature in every single node. So put this random color, and now as a result, I can detect if I'm in a cycle of a certain cardinality because I can see myself that number of hops away. So here, for example, these two nodes that we previously saw had exactly the same neighborhoods analyzed by a GNN. Now can check, do they see themselves 3 hops away, and therefore tell if they're in a triangle or they're in a 6 cycle. And this very simple addition, along with some theoretical analysis, was enough for Ryoma Sato and his collaborators to publish a paper at SDM. So you can see how in this area, even by just very carefully studying certain failure cases and coming up with principled ways to deal with them, you can actually end up with top-tier publications. And this randomized feature idea can be extended more generally to positional features, where you don't just put arbitrary numbers, but you put numbers that depend on a certain kind of positional information in the graph. So RPGNNs, PGNNs are 2 very popular examples of this. And also, if you know that certain substructures, for example, rings in chemistry, are going to be super important, you can literally just count them and add that as extra features within your input nodes. And this is exactly the subgraph isomorphism counting approach from Buritsas and others. And just generally, as I mentioned, looking at these failure cases of the one Weisfeiler-Lehman test and fixing them within GNNs yields these classes of higher order GNNs. And depending on how you do it, you can categorize the approaches into 3 broad groups. You can either do as we did above and modify the features of the graph. So put randomized features or positional features or count interesting subgraphs. Or you can use the graph structure to modify the message passing rule, like directional graph networks, which used the graph Laplacian information to change how the messages are passed. Or, and in my opinion, this one is the most exciting, you can actually use the structure of the graph and the information on what you want to do with the graph to modify the graph over which you're doing the message passing. So structures such as 1 through 3 GNNs that compute messages not only for the nodes, but also compute them over tuples of nodes are strictly more powerful than the Weisfeiler test, and obviously a bit harder to scale, but present one particular way in which you can go about doing this in an efficient and principled way. And very briefly, I'd like to remark that everything we've said here about the one Weisfeiler-Lehman test and so on assumes that the features are discrete. But very often in the real world, features that you have are not going to be discrete. They're going to be continuous, either as part of latent states of a GNN or just generally noise you get from the real world. And actually, if features are continuous, the proof of the sum being the best one, the injective one, and on which all this expressivity claims hinge, falls apart. And here I've given you just a few examples of where the features within a neighborhood are just arbitrary scalars. And depending on how you lay up the neighborhood, you could end up having the sum aggregator fail to distinguish them. And in some cases, you might be able to get away with doing minimizing, maximizing, or taking the standard deviation or something like this. So it seems like depending on how you set up, if your underlying features are real numbers, well, you won't be able to use just the sum aggregation to deal with it. And there doesn't seem to be a winner even in this case. And in fact, in our P&A paper, which we published at last NeurIPS, we prove that there isn't a winner aggregator. In fact, if you want to discriminate between neighborhoods of size n, whose underlying feature set is the set of real numbers, you need at least n aggregators. And in the P&A paper, we also propose to combine various aggregators to reap as much of the theoretical benefits of doing multiple aggregations. So use means, standard deviations, maxima, and minima as a sort of bases and compute all of them at once and concatenate the results. So I think this was the last thing that I wanted to cover for today. So just to recap, we've done a deep dive into graph neural networks, showed the graph network architecture, how it runs over generic attributed graphs. And specifically, we've shown how transformers and deep sets fit within the flavors that we described. And we looked at how can we use latent graph inference to infer a graph for a GNN to use. And then by studying graph isomorphism testing and higher order GNNs and PNA, we've shown how we can break the limits of graph neural network expressive power. For the next set of lectures, we're going to now move beyond graphs and sets and have some much stronger geometric constraints. Specifically, we're going to look at geometric deep learning over grids and homogeneous groups. And you can also expect to hear a bit more about spectral GNNs and the graph Fourier transform in Joan's upcoming lecture on grids. So thank you so much for listening. We have a bit of time to answer questions online, but I will get to everything on Campus Wire anyway. So yeah, thank you so much. And I hope you enjoyed it.
Thank you very much, Peter. So yeah, if anyone has a question, I'm not sure if there were questions in the chat.
There were two.
Okay.
Yeah, I can start with the first one regarding the order of the operations of graph networks. So should we always update edges first and then update the nodes and so on? In this particular setting, it makes the most sense to update the edges first, because the edges are only specified by the two nodes that are adjacent to it. So it's always a fixed number of things that go into computing an edge feature. Whereas when you're updating a node, you're typically seeing the node as the combination of all the edges incident to it. So just from a cardinality perspective, it makes the most sense. That being said, you can change the order of the various operations. However, I think what you'll end up with is basically, I think in the end, like you have to do all these three anyway somehow, and then you have to stack more layers like this. And I think you'll end up with something that's basically equivalent, even if you change the order. So yeah, this was just the principal order that seems to make the most sense implementationally, but yeah. Okay, and right. So Rami, I believe your question on why does HG depend only on HU and HUV, it is from the illustration I did, right? It was from the picture that I drew, right? Yeah. Okay. So basically, what I did there was basically just to illustrate on like a single set of like one edge feature, one node feature, and so on, to draw a diagram to show how these pieces of information relate. HG definitely does depend on HV. So I just did not draw that arrow in order to make the diagram more easy to read. If you remember how I actually drew it, next to the arrow going into HG, I put the O+. Like I said, it's the aggregate of all the nodes. So yes, it depends on HU and HV and all the other H nodes actually. So I just, yeah, didn't draw that arrow explicitly. So does that answer your question? Perfect. Okay. Were there any other questions? I think we have time for maybe one more.
Hi, Peter.
Hello.
About layers connectivity.
Mm-hmm.
How is it here? Oh, we need any assumptions? Or
So
how much?
mm-hmm.
How much enough deeper to get a good performance?
So when you say layers connectivity, do you mean something like the edges in the individual layers, or are you referring to something else?
No, this blueprint for one layer in GNN.
Mm-hmm, mm-hmm. Okay.
I mean connecting different layers.
So something like skip connections and stuff like that, or
maybe updating features. In one layer, we update the feature once time. Yes.
Mm-hmm.
So we need to update the feature again.
Mm-hmm. Okay. Yeah. So basically, typically the way in which you will do these kinds of computations is in something that's known as encode, process, decode. So there will be an encoder.
Computational graph. We need k hops neighbors. Yes.
Yes, exactly. So if you want to see k hops away, you'll need k layers to achieve this. Yes.
Yes.
Yeah.
So can define how much we need deeper. Okay, helps.
That's a good question. So I would say that generally this is a hyperparameter that you need to carefully tune. One thing that's interesting about the graph network model as well is that because you have the HG and you can imagine it as a node that's connected to all the other nodes, that effectively shortens the diameter of any graph to just 2. So in principle, 2 layers are enough to cover everything when you have the global vector, the HG. So that can be one heuristic. Like you can see if adding 2 layers helps, and then from there you can try going deeper until it plateaus, but usually you won't see any extra information like in principle when you go beyond 2 layers. But yeah, generally it's a hyperparameter that you need to carefully tune.
Okay, thank you.
Yeah, so maybe one more question. Does all the successful parts of all techniques of deep learning apply to GNN equally? Like stacking multiple layers, doing skip connection and the rest?
Yeah, that's a very good question. Thanks for asking. First, I would say that skip connections are absolutely necessary as soon as you go a little bit deeper, because graph neural networks suffer from this over smoothing problem, where if you're not careful enough and you stack a lot of layers, your features will just converge to exactly the same features in all the nodes, and then you can do nothing with them. So the skip connection is absolutely necessary to avoid losing the context about the node. And going deeper, especially because of this problem, it used to be really hard to go deeper, okay? And recently we're discovering that if you're very careful with some kind of denoising regularization, which I think is also borrowed from other areas of deep learning, it is possible to train graph neural networks up to 100 or even 1,000 layers. If you search for graph neural networks with 1,000 layers, you'll see some papers about this recently. But yeah, like depth has traditionally been much harder. Like it's possible, but you have to be really careful, and it has to be on the right kind of problem. I would also note that in convolutions, because you can think of the grids, right, the images as a graph where every pixel is connected to the neighbor pixels. The diameter of this graph is really big. So to go from one corner of the image to the other, you have to traverse a very long path. And as a result, you actually need to stack many deep convolutional layers to reach the other nodes. And with graphs, it's more irregular, and most social network graphs are actually super low diameter. Like there, if you might have heard of this, like high-6 theorem that says that any 2 people in the world are connected by at most 6 other people in between. So actually, from a very few number of message passing steps, you're already covering the entire graph. So that's another reason why depth is not always completely necessary. But yeah, great question. I hope that answers it.
Yeah, thank you very much. I have follow-ups, but I prefer putting them on campus wire.
Yeah, happy to answer there.
Yeah, so thank you very much for today.
Yeah, I hope you enjoyed it, and yeah, I look forward to seeing you at the time warping lecture next week.
Yeah. Okay, so have a nice day, and bye everyone.
Bye everyone.